Welcome back to the deep dive. We often talk about getting smarter, faster, but what about AI? Forget what you thought you knew about how AI learns. Today, we're looking at why cutting-edge AI innovation seems kind of trapped inside just a few giant tech companies. It's this thing called the single genius model.
Right, this idea that you need one massive, super expensive setup.
Exactly. But the sources we've dug into, they propose something really different. A radical, almost democratic solution to share AI knowledge, like instantly and way more efficiently.
It's a fascinating approach.
So our mission today is to give you the full picture of this new paradigm shift. Okay, let's unpack this. So when we talk about training these huge state-of-the-art language models, they're built using what our forces are calling the single genius model. It sounds impressive, but it's incredibly expensive, very centralized, and it basically means only a handful of players can really push the boundaries.
That's absolutely right. You can almost picture it like a world champion Olympic athlete, right?
Right.
But they have this exclusive multi-million-dollar training facility nobody else can use.
Okay, yeah.
For AI, that facility is this massive, centralized cluster of really specialized, expensive GPUs. And the research paper we're diving into today is essentially a blueprint for tearing down those walls.
And this disruptive idea is called Swarm Sampling Policy Optimization, or
It is.
SAPO, yeah.
Not the catchiest name, maybe.
No. But the actual mechanism seems brilliant. It's built on this idea of decentralized collective intelligence. The core insight, and this is wild, is that thousands of community members could run this software on just everyday hardware.
Like your MacBook, seriously.
Right, your standard MacBook. And they could still get top-tier results collaboratively. I mean, that feels like a massive shift for, democratizing AI development.
It really is. But to really get why SAPO is such a big deal, we kind of need to understand the problems it's solving, the technical hurdles that make the old way so expensive. When you try to train one giant model by spreading it across, say, thousands of machines, you immediately run into two big, costly problems just because of the scale. First off, there's latency, the communication delay.
Okay.
When the model is huge and centralized, the system is constantly shuffling just massive amounts of data.
Right.
We're talking the model's parameters, its internal knowledge back and forth between all of these GPUs.
Thousands of them.
Thousands. And this creates a really severe communication bottleneck. It just drastically slows down the whole learning process.
I see. So it's like a giant network traffic jam, basically. And the cost is wasted time, wasted energy.
Exactly. Wasted computation, really. And the second big hurdle is synchronization.
Right.
To train that single giant model effectively, all those thousands of devices, they have to maintain a perfectly synchronized copy of the model's knowledge at all times.
That sounds fragile.
It is. It's not just technologically complex. This infrastructure is often brittle, and the financial downside is huge. If even one GPU fails to sync up properly, you often have to just discard the entire batch of computation.
Wow.
Which is incredibly expensive. That operational cost, that fragility, that's the real barrier keeping smaller teams up.
Yeah. Okay, so the old model. Centrally controlled, technologically brittle, super expensive when anything goes wrong. So if that traditional model is slow and breaks easily, how does this new approach, SAPO, how does it get around those hardware limits? You mentioned it's built on reinforcement learning.
That's the key, yeah. The solution is built on reinforcement learning, RL, which is different from other kinds of machine learning. It's about learning through trial and error, not from labeled data.
Like learning to play a video game.
Exactly like that. You let the program play thousands and thousands of times. You don't tell it how to win. You just give it a score, a numerical reward when it does something good. It figures out how to maximize that reward over time.
Okay. And the paper uses 3 core RL terms we need to know to really get SAPO. Maybe I can take the first one.
Go for it.
Okay, first is the policy. You can think of this as the AI's brain, or maybe its strategy at any given moment. It's the function the model uses to decide its next move, its next action. And the whole point of training is simply to make that policy better.
Right, improve the strategy. The second term is rollout.
Rollout.
Think of this as one complete attempt, a single episode or playthrough of the task. So in the context of this research, a rollout is the entire sequence of answers an agent generates for one specific reasoning question. It's the record of what the AI tried to do.
Got it, the attempt. And the third term is the reward.
The feedback score.
The feedback score. In the experiments, they used a really direct system. They had a program called a verifier. Check the answer. If the answer was right, bang, the AI got a reward of 1.
Simple enough.
If it was wrong, it got a 0. This specific setup is called RL with verifiable rewards, or RLVR, because you can definitively check if the answer is right or wrong.
Okay, with those terms, we can actually introduce SAPO itself. It's fundamentally different because it's a decentralized swarm of independent computers nodes working together. It completely ditches the idea of one single monolithic facility.
And this is where it really turns the old model on its head. SAPO radically embraces something called heterogeneity.
Yeah, that's a key point.
We're not talking about a perfectly matched set of supercomputers anymore. These nodes, these computers in the swarm, they can be totally different. One could be a high-end server, another could be just a standard MacBook.
Connected over different internet speeds even.
Right. It works because it operates more like, say, an open source software project where people contribute from everywhere, not like a single, tightly controlled system.
And that flexible, decentralized nature is exactly what unlocks the efficiency gain. The actual learning cycle is this really simple but powerful four-step process. Step 1, individual work. They call it local rollouts. Basically, each node, each computer, works on its own batch of problems. It uses its current policy, its current strategy, to generate its own unique set of experiences, its own rollouts. This is like the individual study phase.
Okay, makes sense. Step 2. Step 2. Sharing discoveries. Broadcasting rollouts. And this seems like the absolute core breakthrough, the thing that kills that communication bottleneck we talked about.
Exactly, because the node does not broadcast its entire massive, complex internal model as policy parameters. That would be slow and heavy.
Right.
Instead, it just shares the experience, the results of its work. And it does this in a really simple, lightweight format, like just a text file. It contains the question it tried, the answers it generated, that's the rollout, and the ground truth correct solution if it found one.
So we're sharing the knowledge, the experience, not the heavy machinery specs.
Precisely. This lightweight exchange of experience is incredibly fast and completely avoids that crippling synchronization and communication bottleneck you get with traditional training. Okay, step 3, collective learning. Assembling the training set. So the node gets all these shared experiences from others. Then it creates its next training data set by sampling a mix. It takes some of its own recent rollouts
Its own work.
and some number of rollouts shared by other nodes in the swarm. And critically, nodes can be smart about this. They can filter the external experiences, maybe choosing to prioritize only the rollouts from others that actually got a high reward, the successful ones.
Ah, okay. So you learn from your own attempts and the successful attempts of others. And finally, step 4, policy update.
Yep. The node learns from this combined data set, its own discoveries, plus the filtered and collected knowledge, and updates its policy, its strategy, hopefully getting smarter for the next round.
The aha moment for me reading this was just how quickly knowledge could spread when the information being shared is just simple, lightweight text. The researchers mentioned this fascinating little detail. They said initially they actually had to give the AI a reward just for formatting its answer correctly.
Right, just getting the structure right.
But they stopped giving that specific reward pretty quickly because knowledge about the correct formatting just spread throughout the swarm almost immediately. One agent figured out a good template, shared it.
And boom, everyone else saw that successful rollout and copied the format. No explicit instruction needed, it just spread organically.
Amazing.
So, to really prove this efficiency claim wasn't just theoretical, the researchers ran a carefully controlled experiment. They used 8 identical clones of a small language model, Quen 2.5 0.5b.
Small language model, so not one of the giant ones, but still capable.
Exactly, and they put them inside this custom testing environment they built called the Reasoning GYM.
And the reasoning GYM is important, right? Because it's not just a list of questions, it's dynamic.
Yes, it's a dynamic problem generator. It creates new problems on the fly, and it has these programmatic verifiers code that can check if the answer is actually correct. This forces the models to develop genuine reasoning skills, not just memorize answers they've seen before.
Okay, smart setup. So they had these 8 identical models. How did they test the collaboration idea? Well, they set up 4 different team strategies. It was all based on how the models built their training batch, which always consisted of 8 total samples, 8 rollouts.
Right.
So first you had the soloist, 8 local samples, 0 external. This guy relied only on its own work, the baseline.
The control group, basically.
Then you had the follow-all, only 2 local, 6 external. This one relied really heavily on what others were sharing.
Leaning on the crowd.
And maybe the most interesting one, the balanced team player. 4 local, 4 external. And even split between its own work and learning from the swarm.
Okay, so soloist, follower, balanced. What happened? The headline result was, well, pretty profound. The four external configuration, the balanced team player, it achieved a total cumulative reward score of 1093.31 over the experiment.
Okay. And the soloist.
Compare that to the isolated baseline, the soloist model working all by itself, it only managed a score of 561.709.
Wait, so 1093 versus 561?
That's a 94% improvement in cumulative reward.
Yeah.
They essentially nearly doubled the learning efficiency just by enabling that balanced sharing.
Wow, a 94% improvement. That's huge. Does that mean you could train a model in, like, half the time, or is it more about saving costs by using cheaper hardware?
It really points towards both, honestly.
Yeah.
But the main takeaway for the learner, for the model, is that incredible acceleration in training time. It's strong validation that sharing experience, not the model itself, but the outcomes, dramatically cuts down the time and resources needed to get good at a task. But what's also really fascinating here is this kind of Goldilocks principle they found, meaning more sharing wasn't automatically better. That 44 balance split significantly outperformed the soloist, 0 external, obviously, but it also significantly outperformed the 26 setup, the follower, which did more sharing.
Huh. So 44 was better than 08, but also better than 26. You needed that sweet spot, not too little sharing, not too much. You have to find the right balance between learning yourself and learning from others. And the performance of that 26 setup, the follower, the one that overshared or over-relied on others, that actually revealed a potential danger, right?
It really did. That setup showed what the paper called steep learning and forgetting behavior, and also strong oscillations in performance.
Steep learning and forgetting, like cramming for a test.
Exactly like that. Think of a student who only crams using their friends' notes, right? They never actually did the foundational reading themselves. They might see this rapid, steep spike in performance just before the test by memorizing known answers.
But they don't really understand it.
Exactly. The knowledge is shallow, it's brittle. As soon as they face a slightly different problem, poof, it's gone. They forgot it. Because they were only exploiting known answers from others, not generating novel solutions themselves.
And the researchers diagnosed this as a kind of tragedy of the commons.
Yeah, that's the analogy they used. When agents are consuming a huge amount of knowledge from the pool, taking 6 external rollouts, but they're only contributing tiny amount of new exploration themselves, only 2 local rollouts, the shared knowledge pool gets depleted of novelty faster than it gets replenished.
So everyone just starts repeating the same old stuff.
Pretty much. Agents just start to echo past successes they saw from others instead of exploring potentially new, maybe even better, solutions. It really hammers home the need for that healthy balance between exploitation, using what the group knows, and individual exploration, trying new things yourself.
Okay, so the controlled experiment showed huge gains with balanced sharing. What about the real world? Did they test this outside the lab?
They did. They ran a large-scale demo involving literally thousands of community members using their own hardware, incredibly diverse setups, running this SAPO software. Performance was tracked by a central judge system.
Thousands of people on regular computers. What did they find?
Key finding one basically confirmed the lab results. SAPO provided statistically significant benefits for those mid-tier models, like the Quen 2.50.5V we saw in the experiment, compared to models running in isolation. Collaboration helped them learn faster in the real world, too.
Okay, that's good confirmation.
But here's where it gets really interesting and a bit more nuanced. When they looked at the stronger models participating in the demo, like a slightly bigger model called Quen 3.0.6D collaboration, didn't seem to help them much at all.
Wait, really? The stronger models didn't benefit?
They performed pretty much the same whether they were participating in the swarm or just operating alone.
Huh. That seems counterintuitive. Why would a stronger AI not benefit from all that collective intelligence that was boosting the mid-tier guys? They called this the expert's dilemma, right?
Exactly, the expert's dilemma. And the likely answer comes down to how the shared information was handled in that big demo. They used uniform random sampling without any filtering.
Meaning the expert AI was just grabbing random experiences shared by anyone.
Precisely.
Yeah.
Think about a world-class human expert, right?
Mm.
They don't improve by just passively listening to random chatter on the internet. They need curated, high-quality, maybe even challenging information from other experts or reliable sources.
Okay, I see.
For that strong AI in the demo, the shared pool of experiences was likely just dominated by noise, by lots of low-quality attempts and basic discoveries made by the much larger number of less capable models in the swarm. The shared experience wasn't helpful. It was just noise.
So the signal-to-noise ratio was too low for the expert.
Exactly. And this points directly to the next steps for this research. If we want SAPO to really benefit the strongest AIs, future versions need to incorporate intelligent filtering.
Like, the AI needs to be able to judge the quality of the shared experience.
Right. Or maybe use trust metrics or reputation systems for the nodes sharing information, something to ensure high-quality knowledge transfer, allowing the expert AI to effectively ignore the random noise and focus on the valuable signals.
Okay, that makes a lot of sense. Filtering is key for experts. Now, the paper mentioned that SAPO itself, the algorithm, is agnostic to data modality. That sounds technical, but it means it doesn't really care what kind of task it's learning, right? Text, images, logic.
Correct. The core mechanisms share lightweight results, learned from the best ones, can apply to lots of different things.
Which opens up some really exciting possibilities for the future that they touched on.
Definitely.
First, they talked about specialized swarms. You could have some AI agents that specialize in really complex areas, like, say, advanced mathematics or symbolic logic.
Hmm.
They could focus their exploration on those hard problems and then share their high-reward rollouts, their successful proofs or solutions, with more generalist AI agents in the swarm.
So the specialists teach the generalists specific skills.
Exactly, leading to much faster knowledge transfer in tricky domains and creating more well-rounded AI systems overall.
That's powerful.
Second, human in the loop. This one blew my mind a little. Since the experience being shared is just simple text, remember the question, the rollout, the solution,
Yeah, the lightweight format.
a human expert could actually craft a perfect solution to a really difficult, maybe real-world problem. They could format it as a high-reward rollout and just submit it to the swarm.
And because it's lightweight.
That incredibly valuable, human-vetted knowledge could propagate to potentially thousands of AI agents almost instantly. Imagine debugging code or solving scientific challenges that way.
Wow, yeah.
Yeah.
Injecting high-quality human expertise directly into the collective learning process.
And finally, maybe the most out there idea, an AI art collective.
Okay, intriguing.
Imagine a swarm, but this time it's image generation models. Each model could be programmed with a slightly different reward function, maybe rewarding a different aesthetic. One likes photorealism, another likes abstract expressionism, another wants, I don't know, surreal cat paintings.
Mm-hmm.
They generate images, get rewards based on their internal taste, and then they share their most successful creations, their high-reward rollouts, the images that really nailed their specific aesthetic.
What would happen?
The paper suggests this could induce a virtuous cycle of creative discovery. Models would be exposed to successful examples from different aesthetics, potentially leading to emergent, entirely new artistic styles that none of the individual agents locked into their own reward functions would have ever discovered alone.
A collective artistic consciousness, almost. That's
Yeah.
pretty cool.
Right. So wrapping up, SAPO feels like much more than just a technical tweak.
Oh, absolutely. It feels like a critical achievement, a potential turning point. It really shows a path to shift AI development away from that monolithic, isolated, incredibly resource-intensive, single genius approach.
Towards something way more efficient, much more scalable, and frankly, more democratic. A truly collaborative paradigm.
Exactly.
The core principle that got validated here seems crystal clear. Collective intelligence, when it's powered by efficient communication and smart sharing of experience, is proving to be superior to isolated genius, at least in the realm of AI training.
The results speak for themselves.
And you know, the entire system, this thing that nearly doubles learning speed for AI, it's all built on finding that right balance between self-reliance, the local exploration, doing your own work, and open communication, sharing your successes effectively.
Mm-hmm. That balance is key.
Which does raise a pretty interesting question for us, doesn't it? If this kind of balanced collaboration is proving so critical for AI's rapid evolution, well, what does that teach us about our own capacity for learning and discovery when we find that right balance between our individual efforts and tapping into the collective knowledge of our peers?
Definitely something to think about.
Something to mull over until our next deep dive.